Hello, my name is Don Goff, and I'd like to welcome you to this presentation on application, monitoring, and quantification of arsenic. Arsenic is an element isolated in 1250, has three allotropes, yellow, gray, and black. It exists in a variety of species. There's inorganic species and organic species. The inorganic species that we'll look at most in this presentation are arsenite, which is arsenic 3, and arsenate, which is arsenic 5. There's also arsine gas, which is very poisonous. In addition, the organic versions, and I've listed some here, given their abbreviations, that we'll use throughout this presentation. The major uses of arsenic include chromated copper arsenate, which is used for pressure-treated lumber, herbicides, pesticides, and insecticides. Though most of these are being phased out or have been phased out, they've been used in the past and have contaminated the soils. They're used in the manufacture of glass, so arsenic is used as a decolorizing agent, also found in pigments for inks and paints. It's also used in semiconductors, such as gallium arsenide. Arsine gas is also used as a doping agent. And more recently, in the last couple of years, cubic boron arsenide has been discovered to be possibly the best semiconductor that there is due to its ability to move electrons and holes better than silicon itself, and also conducts heat much, much better. Inorganic arsenic species are very potent toxins. What we have here on the right is a potential lethal dose of arsenic trioxide. It can be lethal from doses as small as 1 to 2.5 milligrams per kilogram. However, there have also been reports of some people living with doses as high as 9 milligrams. Organic species of arsenic are generally less toxic than the inorganic species. Inorganic arsenic, such as arsenite, is usually more toxic. One mechanism involving arsenite, it inhibits the pyruvate oxidation pathway. It impairs gluconeogenesis and oxidative phosphorylation by binding to sulfhydryl groups and critical enzymes. Arsenate is very similar to phosphate groups, and what it will do is it will replace the phosphate groups in the very high energy phosphate bonds, such as an ATP or DNA. Chronic exposure, so what I talked about already was the acute exposures, but chronic exposure causes various cancers, including bladder, kidney, skin, liver, prostate, lung cancer. Arsenic is naturally found in the Earth's crust from 2 to 5 parts per million. It's spread naturally into the environment by volcanic activity. However, anthropogenic sources include mining, smelting, wood preservation, burning materials such as coal that may contain arsenic, the glass industry, electronics industry, and so So industrial and agricultural uses have caused contamination. And arsenic is affecting the drinking water for millions of people in over 70 countries. Over 140 million people in nations such as China, United States, India, Bangladesh, and many, many others exceed the level of arsenic set by the World Health Organization of 10 micrograms per liter. And in Bangladesh, 1/5, that's 21.4% of all deaths are caused by arsenicosis. In a recent study involving honeybees from Belgrade, Serbia, they were testing the feasibility of monitoring arsenic species with honeybees. Prior studies with honeybees were only able to determine the total arsenic levels. However, arsenic toxicity differs significantly by speciation. As we said earlier, inorganic arsenic is much more dangerous, much more toxic than the organic forms. And so here's a map where they did the study, and over here you can see this is sample site number 1, and this is where they had a small village. It's a small agricultural village. Over here, sampling site number 2 is actually at the University of Belgrade, which is actually in the middle of the city of Belgrade. And then over here, sample site number 3 is near a coal mine, and then over here is sample site number 4, and this is basically an industrial city that produces petrochemicals and fertilizers. And so what they had here was there was 4 different beehives. Beehives from each of these areas were tested. So for sample and collection and preparation, there were 50 to 100 bees collected from each of the locations that I mentioned on the map. The bees were sacrificed at negative 80 degrees Celsius, and they were freeze-dried. The freeze-dried bees, about 50 of them from each location, were homogenized in an ultra-centrifugal mill. They had to determine the total arsenic concentration first, and to determine the total concentration of arsenic, they took approximately 100 grams of the freeze-dried bees. They were carefully measured and placed into quartz vessels that were about 10 milliliters in volume each, and then there was nitric acid added to them in order to digest the bees, and they were digested in an ultraclave 4 microwave digestion system. After digestion, the solutions were diluted to 10% by volume of nitric acid. In addition to that, bovine muscle powder was prepared using the exact same method to use as a reference material. For speciation analysis prep, they needed to make sure that the extraction procedure was valid. So they tried 4 different extraction procedures and evaluated them. One was ultra pure water near room temperature. The second procedure was ultra pure water at 90 degrees Celsius. The third procedure was 20% by volume methanol, and the fourth procedure was 1% by volume formic acid. And it turned out that the pure water at 90 degrees Celsius for 1 hour had a 90% extraction efficiency. And so that is the method that they used. Just to make sure that there was no bias, they actually used bees from at least 3 different locations, and they did everything in triplicate. Extracts so finally the extracts were done at 90 degrees Celsius, and the extracts then were centrifuged and then filtered through a 0.2 micrometer nylon syringe filter. And then the samples were diluted and acidified to 10% by volume of nitric acid. So the total arsenic analysis was performed. So the concentration of extracts were actually run through an inductively coupled plasma mass coupled to a mass spectrometer, and it was done in a collision gas mode with helium gas as the collision gas. The measurements were done at 75 for the mass to charge ratio, and the external calibration. So they had to run external calibration in order to quantify the arsenic, and so they ran calibrations from 0.01 to 5 micrograms per liter. So for the arsenic speciation analysis, in order to run the speciation analysis, the species have to be separated. This was done in a high performance liquid chromatography column, PRP X100 column. And so the mobile phase was an aqueous 20 millimolar ammonium phosphate solution that was buffered to a pH of 6. The reason the buffering was important, or the pH is important, if you look at these species over here to the right, you'll see that the species of this one right here is arsenic 3, and this one here is arsenic 5. You'll see that they have hydrogens, and in this case it's neutral. Okay. However, at various pHs, these hydrogens will come off. Well, it turns out that the arsenic 3 has a pKa for the first hydrogen to come off at 9.23. So it actually has the highest pH before it will become an ion. However, arsenic 5 species are generally down at about pKa of about 2.6. And so the pH is important to make sure which substances are going to flow slower through the column. "20 milliliters were injected, and the flow rate was set to 1 milliliter per minute, and the HPLC was coupled to ICP mass spectrometer. The total arsenic concentrations, this is done, these numbers are mass per dry weight, was highest, significantly higher near the coal-fired power plant, and this may be due to the fact that coal can contain arsenic, and as it's burning, it settles down in the area at 367 micrograms per kilogram. And then second at the University of Belgrade, and then finally significantly lower concentrations of total arsenic were found in the village and industrial city. Here we have a power plant chromatogram. So for the speciation concentrations, it seemed as if the speciation plan did work. It accounted for about 73% of the total arsenic. So all of the mass of the species accounted for 73% of the total arsenic. The power plant, village, and university had 95% in organic species, which are the most toxic. The industrial city, however, varied a little bit. It was 80% inorganic and 15% DMA, which is an organic form. How would I teach this to my students? First of all, my science department does not have access to HPLC or ICP-MS, so the concepts will have to be taught separately. I would teach chromatography first through liquid paper chromatography, using doing a chromatography lab with inks. I would use water-soluble inks like the vis-a-vis markers, and also alcohol-soluble markers such as colored permanent markers. Moving on from there, I found a lab that is a homemade column chromatography lab. The column is made with a 10 milliliter baby dosing syringe, a stationary phase, cotton ball or glass wool shoved into about 1 milliliter of the base, and then wetted, and then tamped down. And then toddler sand is clean, it's very fine, it doesn't have any impurities, and so adding toddler sand up to about the 8 milliliter mark, and then wetting it down with water, and then finally the mobile phase that would be used is 70% isopropyl alcohol. So about 1 to 2 milliliters of the analytes. In this case, I would teach using a mixture of dyes, and the key here is to make sure that there's always liquid above the sand, and so the dyes would be placed on top of the sand, and then isopropyl alcohol would continually be added using transfer pipettes, and then as it flows through, the samples can be collected into ice cube trays, or if you had large enough spot plate wells, but most likely these ice cube trays. And if you get enough of them, then you can see the separation of the dyes. To simulate the ICP part of it, this lab would be performed after the Bohr model had been explained in Spectroscope's lab that I do in class with gas tubes, also with the spectroscopes. Then a demonstration of flame ionization using a Bunsen burner. I found a safer version of this is now being promoted by the American Chemical Society, where wood splints are used, soaked in the about 0.1 molar solutions of the various ions or metals that you want to test for. And then this is a way to show how we can test for metals. I would not test with arsenic, as that would be dangerous, but I would just use more inert metals, as you can see on the screen over here, such as sodium or potassium, lithium, and such. And then I would explain the advantages of inductively coupled plasma as having less background color or light, also having the ability to excite more and more atoms. One of the reasons it's tough to see potassium is because of the transitions just don't happen nearly as often. All right, finally, I would have to show them some actual data from a time of flight mass spectrometer. So this is actually, I obtained this picture over to the right. It was another study that was done. And in this case, they used also, they showed fragmentation using a electron spray. And one of the things that we do early in AP chemistry or dual credit is to look at mass spectroscopy, ionization, and fragmentation of organic compounds. And so this would be done also after that unit. So arsenic speciation in tree moss was the study that I was referring to. And to the right, you can see the graph. And HPLC hyphenated with ICP MS was used for quantification. And then, so I can explain that to them. And then electrospray ionization quadrupole time of flight mass spectroscopy was used, and that causes fragmentation. And that was used, I don't know if you can see over here that this is a form of a sugar form of an arsenic species. It was an unknown that was determined, the structure was determined through the fragmentation. Thank you for watching this presentation. Here are my references. Thank you.